All right, so yeah, let's get started. Welcome everyone to this distinguished lecture in the distinguished lecture series of ELLIS. It's my great honor to introduce Mira Mezini, who's a professor at TU Darmstadt, and not just a professor, but a Löwe distinguished professor. Mira has done really interesting work in the area of software engineering, programming languages, and intersections with AI. She has won more awards than I'm willing to list now, so let me just give you a selection. So she has been awarded an ESC Advanced Grant, a Google Research Award, the 2025 Senior Dahl Neigert Prize, which is one of the most prestigious awards in the SEPL area, and she's also an ACM Fellow. She's also held various leadership positions in bigger projects at TU Darmstadt and beyond. And most recently, I'd like to note the DFG Excellence Cluster that she's co-leading on reasonable AI. And that also connects well to the presentation she's going to give today, which is on AI-assisted software development. Before she starts, just two administrative notes. So there will be a sheet of paper going around. If you're here for the Hauptseminar, then you need to check the last column. And if you want to ask any questions later on, just wait a second to get this microphone, because we are recording the talk, and otherwise your question is not on the record. And with this, I'm very happy to introduce Mira. So let's welcome her. And
thank you for the invitation to the Distinguished Lecture Series, and thank you, Michael, for the presentation. As Michael already mentioned, I am a software engineer and programming language researcher from background, but not really recently, I will say a few words during the talk, since quite a while also worked at the intersection between software engineering, programming languages, and AI. The talk today will be organized in 3 parts. They are not very balanced in terms of the size. I will start with a quick overview of opportunities for AI-driven, AI-based software development, expectations we all have in this area, but also mention a little bit of some hypes. To move to the second part and explain why I say hypes, because there are some hard truths, there are some problems still that we have to solve. And in the third part, I will look ahead in the sense of present some of ongoing projects in my lab in this area and a bit of the excellence cluster at the very end. Okay, dreams and hypes. AI-assisted software development is kind of everywhere. The idea here is very roughly, essentially, you have large language models. When we say AI, we're saying Gen AI at the moment. You have large language models trained also on code that are behind some integrated development environment, and you have developers that communicate via the IDE with the model behind the scenes, or maybe use the model directly via an API. And there are many tasks where AI is supporting, code generation being one of them, very popular, but also code summarization, code translation, test case generation. Michael has done quite some work there, but program repair, vulnerability detection, you name it. And I just put a paper there, which is kind of a survey of how AI and large language models in particular are being used for software engineering. Why is this popularity? I think one of the main reasons is that everybody, developers, anticipate increased productivity by using these tools. And this shows up in, for example, the most recent survey, developer survey of Stack Overflow, where basically, almost like 76% of the developers said that they are using or will be using soon large language models during their software development project. And then the reason being a productivity or expected productivity increase. But there is this other thing, which is potential for wider access, democratization of programming and software development. Here I just put, there is this video, which I'm not going to play, an 8 years old girl programming a website to say hello to Harry Potter, and it went kind of viral on the internet because it was also retweeted, this post by Jeff Dean, saying that writing significant software systems using natural language instead of computer-oriented programming languages is one of the most significant aspects of generative models. It opens up the ability to get computers to do what you want to many more people. And let me see. Another great potential that I see is that with these large language models or code models, we might be able to close the gap, the chasm between specifications and implementations. You don't need to look at all the parts of this cartoon. It's rather complex. It's used very often in software engineering projects to kind of illustrate the discrepancy between what customers explained, what they wanted to have, what the developers, the software team ended up implementing, and at the end, after the customer gets what is implemented, the customer realizes actually he or she wanted completely something else. So if we have the possibility in the future to have specifications written down in naturalistic language, I call it naturalistic purposely, so kind of a language that feels very natural, but still I believe it has to be a little bit more formal, that arbitrary natural language. We might, and then have a machinery behind these naturalistic languages that generates implementations in towards different platforms. This might close the chasm and make domain experts into software developers in naturalistic programming languages. So seen from my perspective, from the background, from the work I have done in the past, one could ask, okay, dreams coming true? What I mean by this is that very early, actually, in 2006 already, we talked about this naturalistic programming. So programming in, let me see whether this works with the video. Yes, in natural feeling language. It was still a programming language, that's why naturalistic, a formal language, but inspired by natural languages, kind of inheriting a lot of concepts from natural languages. And indeed, you could give the system statements in natural language and then have these statements be executed automatically. This work, unfortunately, we didn't continue with the work because I think we hit the wall of natural language understanding at that point. And very unfortunately, the PhD student even never finished, although I have his PhD in my office, almost 300 pages, but he was very ambitious to implement all of it, although I said several times, you don't need to implement all of it, you just make explicit what is implemented, what is still not implemented, but okay, he stayed on his own way. Another work that you could say, okay, dreams coming through is our very early work on intelligent code completion. Goes back to a paper in 2009, the work started before that, and the idea there to use machine learning algorithms, in that case it was clustering algorithms, to make code completion more intelligent. What does it mean? At that time, in early days of code completion, basically, here's an example in Eclipse, in the IDE we were working on at that time, and you are working with a text object, and if you ask the IDE at the moment, what are my options here, you probably would get this many options, and it's, of course, clear that yeah, that's not an effective way of supporting developers, and there are other objects that in this library, which have even a larger amount of options to provide. And with our work, we were able to reduce, in this concrete example, to just 3 most probable methods that would be relevant at the context where the developer was asking the IDE for help. And actually, we went further beyond code completion and had this idea or vision, which we coined IDE, Integrated Development Environment 2.0 at that time. I think this is a paper in 2012 at ICSI NEAR workshop, where we had this idea there is so much knowledge about software development, about code documentation, developer forums out there. What if we collect all this knowledge, process it, and provide insights to the IDE of the developer? And basically, more or less, I mean, this is essentially what we have today with the large language models behind an IDE. This was the Code Recommenders project, was an open source, official open source project under Eclipse. It was distributed with Eclipse at that time, so in that sense, it was very successful in terms of papers, but also in terms of transfer. We also founded a company called Code Trails at that time, which was relatively early sold to JetBrains. At that time, it was difficult to convince people, I have to say, that this code recommendations based on probabilistic methods are something everybody found this exciting, but when it came to really start projects, it was kind of difficult. Okay, at least, I mean, in terms of scientific recognition, this work got quite some recognition with the most impactful paper award in 2024, which we received at ICSI. This is a SIGSOFT award. And also, it's also mentioned in my ACM Fellow citation for contributions to learning-based code completion. Now, from there to now, what is different? And basically, if I reduced it to one word, it's basically size. When we received the Most Impact Paper Award, the Marcel Bruch, now with JetBrains, the person that did the PhD in this topic at that time, sent me a message saying, pretty cool to see how much of what we imagined years ago has become reality. And what I want to emphasize is this, like, and also crazy, how primitive our means were at that times with models of the size 50 to 2,000 parameters compared to the trillions parameters we have today. So basically, this scaling hypothesis is the key of the success where we are today. Of course, also some algorithmic developments like this self-supervised pre-training, fine-tuning with label data, and reinforcement learning based on human feedback. And in Darmstadt and Hessian AI, which is the Hessian Center for Artificial Intelligence, we also play around with scale, of course, not the scale of OpenAI and the like, but still for a university site, we have our own supercomputer of roughly 35 to 40 million euros to play around. And that's the scaling has had tremendous effect also when it comes to AI for software development. But are we at the verge of having AI replace software engineers? Some people, very renowned persons, also kind of claim this. Of course, these two guys do it for particular reasons, I think, because they need to sell GPUs and language models. But I find this kind of dangerous because people have started thinking, oh, do I need to study computer science at all? Because machines are doing the software development. And I think this is wrong for several reasons. That's why I will go very briefly now and have a look at what are the problems we have today. So we are not there to say AI is replacing software development, software developers, and deep expertise in software engineering for several reasons. First of all, so there are several studies out there. I just cited one of them here, published at Security and Privacy Conference, the IEEE conference, and also featured as one of the highlights at the Communications of ACM, basically saying 40% roughly of the Copilot generated code has security issues. And then there was another paper at CCS, I believe, yes, doing a user study, basically having two teams of software developers working on the same project, one team with using AI systems and another one without such systems. And basically what they found out is that the team that was using the AI system produced less secure code, but was much more confident that their code was more secure than the other team. So this kind of erroneous self-confidence, which is problematic. And a more recent paper, it's ICLR, I think, 2025, looked at the capabilities of large models to generate backend software. So the idea here being we have many benchmarks that look at the capability of models to generate, say, individual functions, or make code edits, or solve algorithmic coding tasks. But the goal here was, in order to achieve full automation, LLMs should be able to generate production quality, self-contained application modules, and they selected to look at the backend platforms and backend software for several reasons. Well, first, it's more complex. Second, is security critical, and more difficult to get right and practically relevant. And basically what they found is that even the best large language model, state of the art, that they looked at, this was OpenAI 01, produces 62% of the generated code has errors in it, and more than half of the correct code has security issues. They proposed this benchmark in order to test the capabilities, as I said, for producing backend software. And then basically concluding that we need more targeted efforts to produce such benchmarks that test real capabilities for automation. And also one of the conclusions was that we need targeted efforts to improve the quality of the generated code. And there are many papers. I just featured these 3 so far with a bit of focus on security, but there are many papers out there that kind of talk about problems and issues with code generated with LLMs. And the problem is also that these issues, they come at scale, in the sense that there is another study from this year that looked at AI Copilot code quality, and basically did by GitClear. This was studying real software produced open source or even closed source by enterprises hosting their code in GitClear. And basically what they find out is that there is a lot of duplication out there produced by AI. So there is a lot of copy and paste. And actually what I tell my students in the first lecture is this principle, don't repeat yourself, also called DRY for short. So in the moment you find yourself wanting to write the same code again, think about abstractions that you could define, so that you define those abstractions once and reuse them everywhere. And this means the issues come at scale if we keep generating code and copy and pasting code at this scale. Okay, and these issues show up also in developer surveys, the same survey that I referred to in the beginning, Stack Overflow from this year, saying that developers, you see here, only 3.1% of the developers really strongly trust the results produced by AI generators. And one of the main reasons for the frustration is that the generated code is very often almost correct. So there is a lot of effort that developers need to put in checking, testing, verifying the quality of the generated code. So in general, I believe we will produce faster, we will spend less time in producing code or any other artifact, but the same amount of time, even more, will go into checking the quality and verifying the quality of the produced artifacts. And also we need many more, we need real studies to assess the productivity claim. Personally, I haven't seen really systematic studies out there to show that productivity increase is real. There is this one study that I found, but I don't think it's systematic enough. What they find is that the expectation was of the developers that they will have an increase on productivity by 24%, but at the end, the reality was that the task took 90% longer than without the AI. I mean, this is to be taken with a grain of salt, because the study is really not systematic. It's just to say that we need also for these claims more systematic studies. And this Twitter post by Gary Marcus is basically Andrea Caparti, the guy that coined the term vibe coding, that meaning you write in natural language and you get the code produced, was asked whether he produced some software, and it was asked whether he used AI to produce the code, and basically he's saying, good question, is basically entirely handwritten. So even he finds out that he used Claude and Codex agent, but they were not able to generate code for the complex tasks at hand. Okay, so to conclude that part, going back to in the future, software developers will be replaced by AI. My answer to these claims is that we will need more and not less software developers. AI is raising the level of abstraction at which we do software development, and will be a very important assistant for software developers, but we will need more developers to check and verify the results. We'll need more expertise to make these tools more reliable. If those are the compilers of the future, we better take them very seriously and make them more trustworthy. We will need more deep expertise, I believe PL expertise, to design naturalistic languages for prompting, a bit more structured than what we have today, so that we have these domain-specific naturalistic languages in which we can write specifications. Our domain experts can write specifications that are executable. And at the end, if domain experts are enabled to write specifications that are executable, they turned out to be software developers, so there will be more of them out there, not less. But yeah, so I really believe that we, and also the software engineering community, need to join the game of improving large language models and code models, improving the AI behind the generation systems to make them more reliable for coding. And that's what the biggest part of the talk will be about. With my group, we are looking at advancing what I call machine coders, making them better understand code semantics and thus being more reliable in coding tasks. And I will go through a few projects going on right now, some of them in the very beginning. The first project I want to mention is this project where we constrain the code generation using symbolic rules. The context in which we do it right now is for improving the quality of web API integration code that is generated by existing language models. We have developed a benchmark for checking the quality of the generated API integration, web API integration code, as well as a technique to improve the quality, to improve the results that we find out. The benchmark was just published at AIware 2025. But what's the problem first? So web APIs are very important software modules out there, and of course, it's very important to be able to integrate them with ease, like putting together Google Calendar and Slack modules into a more complex software module. And I mean, the API management market is raising the size, showing the importance of this kind of software, integration software. The question is, how do I use the existing APIs when I integrate them in a correct way? And it's well known in software engineering that using APIs in general is, in a correct way, is challenging. There are a lot of studies showing that typically developers make a lot of mistakes and in all kinds of APIs. I've done quite some work on secure usage of crypto APIs, but the web APIs are even more complex. And there are, the good thing in that part is that there are specifications out there. When we looked at crypto APIs, we had ourselves to write the specification, how correctly to use a crypto API, the Java crypto API in that case. In the case of web APIs, the good news is that there is a standard out there, and the web API providers have the possibility or do provide specifications of how to use APIs in a correct way. The trick there is that these API specifications are very long. The extreme case of Slack is like almost 700 pages of specifications. So understanding these specifications and making use of it is challenging also. So the question is, can large language models help us in this tedious task and automate the integration code? I mean, of course they can. The question is, with what quality, and that's what we checked with our benchmark. So the question was, how correct is LLM-generated web API invocation code, and what kind of errors are commonly made? So for this, we developed an evaluation pipeline, we developed a benchmark, and then let the also state-of-the-art LLMs generate code. We had an execution-based metric. I mean, of course, you cannot just call some web API. We had to do something around it with wrappers so that we could register the configuration to be used for the call without making the call itself. That's this code execution step. And then at the end, given the benchmark and the generated configuration, we could compare the two together. So we used high-end LLM to generate our benchmark because it was not easy to find real code in a way that we could use. Of course, there is a lot of real code using those APIs out there, but in terms of making a benchmark out of them, we used Gemini, the high-end model there, to generate, and then went through a manual creation process for the data set, for the data creation. Then we tested more than 20 models with zero-shot prompting and greedy decoding. The result was kind of a configuration, a mock of the executable code, which we could compare then with the configuration generated by Gemini in our benchmark. Not so exciting. I mean, the interesting thing is the results that we had. I mean, these are a little bit complex, the plots to interpret, but maybe you want to just look at that corner. There are two setups. One where we let the models generate the complete integration code, and another one when we provide the URL to the service API and the endpoint, then let the LLM guess the arguments or complement the arguments. And you can see that the upper line here is it's OpenAPI, OpenAI, not OpenAPI 4, I believe. I have to GPT 4.0 exactly, which has pretty good results, up to almost 90% correctness rates. But if you look at the other models that are smaller, open source, but there is also Meta with a lot of parameters under the models that we tested, the results are pretty disappointing. Less than, you can see here is like 30% correctness rates for most of the models. And we checked several things. We made a very detailed, fine-grained assessment looking at what kind of problems. I mean, correctness is the aggregation of the problems, but then we looked at does the model produce the right number of arguments, the right types of arguments, and so on and so forth. So overall correctness that we found is low. A lot of hallucinated endpoints and parameters that actually do not exist. And typically, I mean, many API invocations that were generated violate the specification. So this benchmark can be used now to check other models because it's very automated. The next step that we did was like, can we constrain, can we force the model to comply with the usage specification? And what we did there, we used constraint decoding, developed a constraint decoding engine for this particular purpose, basically starting with the API specifications, open API specifications. We developed, if you want, kind of a compiler, a constraint translator. From this natural language specifications, we generate formal constraints, rather complex regexes, nested, and so on and so forth. And then during the decoding phase, we constrain the tokens that can be generated. Only those that do not violate the specification are allowed to be generated. That means we have a guarantee that what is produced complies with the specification. And what we observed was a huge gain in correctness. You see all these green parts of the plots. This is the amount of improvements that we achieved. And what to keep in mind is that there are no hallucinations guaranteed. We are looking also at alternative models like reg-based, and I think Michael has looked at reg-based approaches or fine-tuning, but from the very beginning, there are conceptual differences in the sense that both these two alternative methods cannot provide guarantees. And then they have some other disadvantages, like fine-tuning is costly, and API specifications also tend to change, so you will have to do fine-tuning over and over again. When it comes to the reg-based approaches, the problem is that you will have to copy part of the specification into prompt and eat up context space, which is limited. So Gemini that we use Gemini for the benchmark because it has a very big context. And even if you assume big context, then there's it's no certainty, no guarantee that the model will pick the right bits of information from the specification. So basically, to summarize, it's like by using constraint decoding, combining neural and symbolic approaches with each other, we were able to raise the level of correctness even for smaller models, bring it to, let's say, to GPT-04. Another ongoing work, which I'm very excited about, is looking at alternative architectures. So when we say Gen AI, we say transformers. Basically, these are the architectures that are behind large language models, all of these. So state-of-the-art models that are out there. We are exploring kind of an alternative architecture, which is not as well known as transformers, which is called state space models. They come from the area of control systems, dynamic systems, and signal processing. The state space model unit itself basically is a mathematical framework for modeling dynamic systems. They build an internal state, and a state machine, have the mathematics behind it for governing the state transitions. The hidden state at each step depends on the previous state and on the input, and the output generation also depends on the current state. They are emerging. So the idea here is basically, these are very, very small pictures, but you replace the attention layer with a state space model layer. If you go from transformers to the state space models, very roughly. And Mamba is one of the most prominent examples out there for generative state space model. The difference to transformers is that they built this state space-based models. They built a compact memory of what has been seen, while transformers have to look at the entire sequence in the context. So there are some trade-offs, there are some pros and cons, some differences in characteristics between state space models and transformers. Probably the most interesting is that while transformers have time complexity quadratic in the sequence length, state space have linear complexity because they build this internal state. They kind of build a compact representation of what the model has seen so far. There are trade-offs that come with this. They lose some precision compared to transformers, so that's where they excel in handling very long sequences, while transformers excel in exact copying and exact information retrieval. But this quadratic versus linear time complexity means that while transformers are poor at long-range dependency understanding, that's where state space models excel. They are very good at it. Inference time is also better for state space models, and also memory requirements. We will see it in the experiments that we did for code models. So when it comes to software development, it seems like they have some interesting characteristics because for example, we have deployment constraints. If we use the models behind the IDEs are interactive development environment tools, so you cannot wait forever. It's important that the developer gets an answer quickly. We need to handle large contexts when we develop code in the context of a repository level, and many code understanding tasks don't require full quadratic attention. So these are all hypotheses. This was our question, do the theoretical advantages of state space models show in code? And that's why we trained ourselves a small model based on an existing state space model. We fine-tuned that existing model for code. And the goal here was not to develop a state-of-the-art model for code, right? The goal was to have a small enough model that allows us to explore, to investigate research questions, to do so quickly. Things like investigate advantages and disadvantages of state space models for code understanding, looking at whether the theoretical advantages translate to improvements in downstream tasks, in empirical improvements, and also wanted to look at some architectural variations with the state space architecture. And also what we haven't done but want to do in the future, it's hypothesized that the state space models, they have a more explainable mathematics behind it, very well studied mathematics in the control theory and signal processing, and the hope is that maybe this mathematics can be also used to better explain what the model is producing, why, or do even integrate some verification methods directly into training, like model checking, which also works on state machines. So basically, we trained this code SSM model with 2 data sets for purposes of empirical comparison to existing models and for empirical comparison or investigation of the ability to improve with the amount of data and also the ability to generalize to context lengths during fine-tuning, during downstream task training that were not seen during the pre-training. So these are existing code data sets, code SearchNet for 6 programming languages, and StarCoder is a much bigger data set. We took the first one was important because we wanted to compare to existing architectures like CodeBird that are trained on that data set. So I will come to say a few words about the baselines that we used, which we trained ourselves 2 transformer models to make things comparable, to compare apples with apples. But we also looked at models where we cannot retrain, that are out there, like CodeBird, Unix Coder, Graph CodeBird, and Codify. These are models that have been fine-tuned for code. And what to notice here is that we are comparing against, a bit biased against ourselves, because as you see here, all other models that exist out there are trained with much more data and with more complex training objectives, self-supervision training objectives. Okay, but now to the benchmarks. As I said, we looked at several downstream tasks, retrieval tasks, like retrieve code that corresponds to some natural language description, look at Stack Overflow question and answering, benchmarks. These are all existing data sets for benchmarking the quality of the models, for retrieval, for sequence classification. Here we looked at vulnerability detection and complexity prediction, code clone detection, and token level classification. In that case, the goal was to predict the type of some variable in TypeScript. As I mentioned, we trained ourselves equivalent or transformers, BERT coder based on the BERT model with 1024 hidden representation size, the same as we used for some version of the code SSM. Used the same data set here, and then another architecture where we have rotational positional encoding, which allows transformers also to generalize a bit with the context size, so that we could compare the ability of the code SSM to generalize with on context size compared to some equivalent transformer architecture. The results are very interesting, very encouraging, I would say. So in terms of the benchmark, downstream task benchmarking, you could see that out of 7 tasks, downstream tasks, coding tasks, we looked at code SSM provides better results than the other 2 transformer-based models, and the only exception is type inference. Our guess there are several assumptions, but the most important one is probably that it's known that that state space models are very good at long-range dependency understanding, but not so good at short-range dependency understanding, and for type inference you need both of them. Another factor might be that the fine-tuning for that particular task uses much more data, has much more data available compared to the other tasks, and we will see that transformers perform better than our state space model when it comes to large data sets being available. We observed that the state space, our code SSM, is much more efficient in terms of memory and in terms of throughput compared to the raw coder transformer model. We use 64 almost % less, need less memory than the equivalent transformer model. And the very interesting thing is also the sample efficiency. So what does it mean? The state space model achieves more than half of the accuracy, 50% of accuracies, in only 3,000 steps with only 96,000 samples. And when it comes towards the end, this is the comparison with the CodeBird, which we call BERT Coder. So based on BERT, our own trained model, BERT Coder kind of outperforms a little bit by 2 or 3%, I think, when it has seen huge amount of data. But as you see in this part of the plots, CodeSSM achieves very high accuracy very fast. So it's very sample efficient with very much less data. So it's very sample efficient. These results are very encouraging. So that the next step, what we are looking at, is really to look at producing state-of-the-art models. So models that are not just for exploring and for research, but a model that really can compete with larger models. And it's generative. So CodeSSM is only encoder-based. So there is no code generation. It's only code understanding task. All the benchmarks, the downstream tasks we used it for, are about code understanding, not code generation. So in the next step, we are looking at also designing. I think it would be very interesting to look at designing self-supervision objectives that are more specific to code. So far, these objectives all are designed for natural language understanding, not for code understanding. And it would be very interesting to see whether, if we design such objectives for training that are code specific, whether the results are better, become better. Okay. Another project that is in the very beginning, I would say, is investigating the extent to which we can infuse code graph structures to existing LLMs that were trained either on pure natural language data or on code, but with flattened code structure. The motivation for this was a paper we published last year at ACL Findings, a critical study of what code LLMs do and do not learn. And interestingly, there was another paper by our colleagues that was published almost at the same time. Yeah, it's the same time, August 24, in 2 different venues. We used different methods, but came to the same or similar results. The question was, do relationships between code elements captured by models match with relation captured in AST or data flow graphs? So in software, typically the semantics of the execution is very often represented, modeled by graphs, like control flow graphs, data flow graphs, and so on. And the question is, is there a match between the structure, the elements of code captured by models, and those that are captured in AST and data flow and control flow graphs? And basically, the take-home message of both studies, we used different methods. So both, I think, we looked at the attention layers, but also at hidden representation, and they looked at hidden representation, but in a different way. But the take-home messages were similar, that LLMs do not capture code-specific information well enough. For example, the connection between keywords and the identifiers in, let's say, a control structure, like an if-then-else statement. So things that should have more attention to each other didn't have that particular attention we realized that they should have. And starting with this finding, the idea was, can we consider code graphs, as I said, abstract syntax trees, data flow graphs, control flow graphs, and so on, as a modality of itself. So typically, even models that are trained on code, like CodeBird or even Graph CodeBird that has graph in it, they flatten the graph structure. So they use these graphs in their training data, but they are turned into sequences. Our goal was here to keep the structure and to not flatten it, and see whether by maintaining that structure, training graph neural networks on it, and then fusing the parameters of the graph neural networks and the language models brings improvement in performance. As I said, the work is in the beginning, so we are looking at small models right now for doing the fusion, and only at one language, Java in that case, and only AST and data flow graphs. Basically, I mean, the picture is very complex, but basically what we do, given the code, we generate those graphs. We use static analysis tools to extract, I have to say, not generate, extract the graphs. Once we have the graphs, we train very simple graph neural networks so that we kind of aggregate this graph knowledge. And then, this is very complex, we fuse an existing transformer model with these GNNs. We fuse the GNN parameters at the last layers of the LLM. This turned out empirically to work best, but there is a lot of exploration there still to be made, to be done, kind of fusing the parameters of the two models. And the results are, again, very encouraging. They are preliminary, of course, because we haven't looked at large models. The models we are looking at, like CodeBird and Graph CodeBird, Unix Coder, and PLBART, are not the biggest models out there, right? But we want to explore first with these smaller models and see whether what we find out generalizes to larger models. And in terms of capturing the structure, this study I mentioned, we observed that larger models are even worse than smaller models in terms of capturing the structure that they should capture from code. Okay, what to take home from this rather big table is that, as you see, we have BERT and then BERT with the GNNs fused, and Roberta with the GNN fused. The upper part, these are models that are trained on natural language. The lower part are models trained on programming languages, trained on code. And the take-home message is that everywhere the GNN versions of the original models perform better in terms of metrics like bleu, code bleu, or exact match. Now, this, again, has to be taken with a grain of salt, because I'm not a big fan of using these kind of metrics to compare code. But it's a beginning. And it's used out there. I mean, these are the metrics that are used out there. So the take-home message is the quality of the models improves with the graph neural networks infused. And the other important take-home message is the sample efficiency. I mean, the table is a bit hard to interpret, but the take-home message is we compare, let's say, CodeBird versus Roberta. CodeBird is a fine-tuned model of Roberta, and we compare Roberta with our fusion against the Roberta original. And we have, I mean, much better quality in terms of the blue score, but at a much less cost, because to go from Roberta to CodeBird, there you need many more steps for training and many more samples. So we have less training, less samples, and produce better results with the GNNs. So it seems like a very interesting, encouraging result, but there is a lot of work still to be done. Going to larger models, looking at other tasks. We looked only at code generation, quality of code generation in that case. And also kind of measuring, using this probing of hidden representations, again, the same method to see whether the results become better after the GNNs are fused there. Okay, I need to check that, but I'm still okay with the time, right?
Yeah, that was 55 minutes so far. So
okay. We are also looking, just to give you an overview of what we are doing right now, we are also looking at benchmarking. So I mentioned the benchmark for testing the quality of web API integration code generated by LLMs. This is kind of creating and providing a new benchmark out there because there wasn't one for our particular purpose. But we are also looking at existing benchmarks. And I just said I'm not a big fan of using BLEU or even code BLEU for comparing code quality. And one of the cases where it doesn't work is when you use these metrics, these benchmarks, for judging the quality of code translations. I think last year Meta came up with the LLM compiler, as they called, so a model that, based on their model, were fine-tuned for compiler optimization tasks. The goal being, as the name says, LLM compiler, performing tasks that typically a compiler does. And one of the tasks for which code LLM compiler was trained was decompilation, starting with assembly code, lifting it into LLVM, intermediate representation. And then they used the BLEU score to come to the conclusion that their model performed very well because it had 96 BLEU score was calculated during their evaluation, which is pretty high. The paper was even published at the compiler conference, the CC conference. We kind of questioned this, and the idea being, well, I did say this, that we need other methods to judging the quality of an LLM compiler. Why not look at methods that have been used for compiler testing, right? Like in the area, the C programming language and C compilers, there is SIGSOFT, a tool used to check the quality, the correctness of the compiler, to test the correctness of the compiler. So you have SIGSOFT producing arbitrary many C programs of different complexity so that it makes sure that it uses a lot of C features to test the compilers, the compiler quality, but also generates the code such that when it is executed, it calculates a checksum, so that's self-testing. So our idea there was to transfer this compiler testing method to neural code translation, and especially code translation like lifting, where semantic equivalence is important. So that's why BLEU is not good in this area conceptually, because two pieces of code that look syntactically very similar or even identical can be semantically very different. So you could have a piece of code in Java and in C doing a loop over an array. They look identical, but their semantics is very different because one has array out of bound checks, the other language, C, doesn't have. It's not a language with memory management. Okay, so basically what happened is that we used SIGSOFT to generate source code, compile this into binary that, when executed, has produces a checksum. We use the binaries then, provide them to the LLM compiler so that it does lifting to source code. We compile the source code, execute, and then compare the checksums. And if the checksums are the same, then that's a success rate. If not, it's failure. And what we found out is basically that indeed, and we compared the LLM compiler with some heuristic lifters out there that are kind of state-of-the-art in lifting from binary to LLVM intermediate representation. And indeed, we found out that LLM compiler outperforms those heuristic tools out there significantly. But the other thing that this was our goal to find out is that syntactic metrics do not measure well the semantics. At best, there is only a weak correlation between semantic equivalence, measured as we measure it, and the blue score. Which means that, yeah, we hope that then the community kind of takes over this more semantic or execution-based ways to evaluate the quality of LLMs in code translation tasks. And there is a lot of explorations there to be done also for other code translation. Lifting from binary is only one particular use case, very challenging, but still there are others that need more investigation. Okay, and the final thing, kind of a work that we have also just started looking at the benchmarks for evaluating the quality of LLMs in coding, in software development tasks. And basically what we have is the thing that we have the leaderboard, so you have a benchmark, then the models are ranked based on this benchmark. But the ranking doesn't tell much more details about what kind of tasks do models fail to perform well, to what extent can these failures be explained by the complexity of the task, and which task characteristics beyond the complexity influence the LLM. So going more into details on the investigating why some models fail at certain tasks. And basically we looked at function level tasks, more than 800 of them, 4 popular benchmarks which we investigated, and 6 state-of-the-art LLM models. You see them listed here. You see the benchmarks listed there. The findings, I mean, the take-home messages are, we found some tasks where LLMs constantly failed at. So 114 of these tasks, they failures across the LLMs. The complexity of the task only partially explains the failures, and we basically categorized the tasks where models failed in certain task patterns so that we could then, in the next step, find out how can we improve the benchmarks and the models to target this kind of task where they fail all the time. Yeah, this I mentioned the future directions. And it's just about to start now. We want these different projects to converge into a bigger project called the Secure Coder project, addressing the problem with the security of the generated code. The project has not started. It's kind of a future. It starts in January. It's within the Athena Center for Cybersecurity that we have in Darmstadt, and there are intersections between the two centers, the AI Center and the Athena Center for Cybersecurity. And here we will look at various aspects of generating more secure code, starting with producing data sets of higher quality in terms of security. In that we use vulnerability scanners that do exist out there, static dynamic analysis, all of that. Then the idea is to train models on those data, but also we are looking at having a code that generates, a code that plays the critique, that is trained to do vulnerability detection, and the two collaborate with each other. We will work on better benchmarks in terms of security, but also at constraining the generation process, constraining the models based on security knowledge that is out there, but also on security first prompting, as we call it, so integrate security measures directly into prompting, and maybe come up with domain-specific languages for prompting to increase the security of the generated code. Okay, with this, I'd like to start concluding the talk and with some concluding remarks. I think this is also a bit the motivation of the excellence cluster on reasonable AI, but we see this theme also in the course of our projects in the area of AI-assisted software development. The bigger, the better. This scaling hypothesis has been very valuable and might still be valuable for a little while in the short terms, but in the long term, we need new AI models, new AI paradigms. We need new algorithmic developments for several reasons, right? I mean, data is not growing, or at least the human-written data is not growing. Performance of the models is plateauing. We are seeing this. And we cannot go scaling forever. The energy demands, I mean, we are braining, kind of using a lot of energy, and then this has huge impacts in terms of economy and in terms of climate. And we have been saying this actually in Darmstadt, in the team, since, I don't know, 6 years or even more. This was the pre-preparation project for the excellence cluster. This was the idea there. We need new paradigms. And people have well-known researchers from all over the world have starting recently to join the team of saying we are not coming to, well, Le Cohen says human-level AI, but just scaling up. I don't know whether we need a human-level AI. We need AI that helps the humans, but whether it has to be human-level AGI, I'm not sure. But the point is, just scaling up will not bring us to better AI systems. And that's basically the idea behind, I mean, the motivation behind RAI. The idea is that we need compositional AIs, AI systems that are composed of different AI methods and different modules, not these huge opaque models, but composable models. And software engineering plays a key role in this project in both ways. I mean, in the sense of using PL methods and software engineering methods for compositionality, and the other way around, to use the better AI methods then for better software, AI-rooted software development. I mean, the idea there is that we want not only AI to become more reasonable, and when we say reasonable, we mean bringing together reasoning and learning, but even beyond that, making it more reasonable in terms of the data that is needed to train the models, in terms of energy that we need, and so on and so forth. And software engineering, as I said, plays in both directions an important role. Also in direction of, I mean, the second line of thought within the excellence cluster is that we will end up with a new paradigm of computing in general, which we call AI-rooted computing. So software development rooted into AI, or databases rooted into AI, and so on and so forth. Yeah, I mean, this is probably everybody refers to when it comes to combining learning and reasoning, to Kahneman's system 1 and system 2. His hypothesis is how our brains works, that they have these two systems, the fast one, the system 1, which kind of corresponds to learning systems in AI, and system 2, the one that takes longer, that makes deeper reasoning. And that's how we think the future of AI will also be. And basically all the projects, I mean, those where we construct new AI for software, are of this kind, if you want. So combining rule-based methods with neural architectures, or combining static symbolic methods for software analysis with neural methods. And with this, I'd like to conclude by saying that I'm very excited and see a lot of substantial opportunities lying ahead of us at the intersection between software engineering and AI research, and as I said, in both directions, producing synergies. Thank you very much, and I'm very happy to get a lot of questions and engage in discussions.
Thanks a lot for the talk. Yeah, we do have time for questions. If you ask a question, I'll run to you, so you can actually use the mic. Maybe I don't run.
Just a question regarding the commenting. Normally, if you do normal programming, you have a lot of commenting in the code. And if you have an AI-generated code, I would suppose that you typically do not have such comments. And so my question would be, how important are when you're training your models, you have the normally handwritten code which has the comments, and how important are the parts of the comments on the code which are embedded in the code compared to the code part themselves?
Very good question. I cannot really give an answer that comes from observations. I would guess that it plays an important role, the comments and the documentation, the names of the methods, the names of the parameters, and so on. So it's also used, we call it adversarial benchmarks. One of them on retrieval is such that the names of the methods and the names of the parameters are removed or are replaced with meaningless names. That is used to see how robust the models are in that sense. So our model turned out to be very robust. So it's an important factor. But to tell you how much is learned from there and there, yeah, it's an interesting question to ask. I don't know how to answer it, how to test it, but...
Maybe just a follow-up question in a different part. You mentioned it already, you touched it a little bit, that the quality of the code, auto-generated code, depends a little bit on the subject the code is about. So if you have an engineering task, you have a science task or whatever. Is there any information which make it more precisely what kind of topics or questions can be more easily coded? I suppose if you want to generate graphics or so, that's very easy. But when it goes to defining a technical process, such as a flow in a porous structure or whatever, that might be more difficult. But is there any overview available?
Whether it's an overview available, what is available is that existing benchmarks look really at function level, algorithmic, like sorting, really smaller scale tasks. The benchmark that I mentioned, they exactly looked at this question: can we check how good are they at generating backend software which runs on the server, which is typically more complex, more security critical, and found out that even the strongest models, as I mentioned, produce 60% of the code is incorrect or has security issues. So people are looking at it. There is room for making this more systematic. There are also benchmarks that look at repository level, so at what extent is the code not a single function, but code that has several files and artifacts in a repository produces, what is the quality there? But there is a lot of room for systematization in that area.
Okay, thanks very much.
Thank you very much for your talk. You alluded a little bit with your last two slides to several questions I noted, but let me still ask you two of them. One is, when I oversimplify a little bit what you said, is then we cannot really rely on AI to do the coding task for us. So I was wondering, to which extent does the software engineering community look rather at amplifying the intelligence of the human coder rather than substituting the human coder? And my impression was that for most of the work that you cited, there is still the tendency to replace the coder rather than make the coder more powerful.
Well, when you say tendency where, I think in the software engineering community, I've seen a lot of work using the models for certain purposes, and also, how to say it, combining them with other tools around for certain software engineering tasks. There is no risk to think of replacing them in that space. But I've seen less of the software engineering community going into the heart of the systems. Things like training new models with coding in mind. And I would like to see more of this. I mean, this has to be done together because this involves a lot of AI machinery, right, to come up with new architectures or change existing architectures. And we need to join forces because the software engineers bring the software engineering knowledge and expertise, which is absolutely necessary. Code is not natural language. It has structure. So we need to go into the heart and bring this, as you say, the software engineers' mindset and knowledge into those systems. Amplify, if I may borrow your term, their capabilities by using software engineering programming language knowledge.
Another question which troubles me also with the kind of work that we are doing, to which extent can we do science when you look at the modern models like GPT and so on, we don't really know what's inside. And there are so many things, different modules that lie inside, that when we evaluate that, using that as a black box, it's a bit unclear what we really evaluate, right? Of course, if you use the simple systems that are freely available, we get some insights, but these are not, as you show, also the state of the art. And so I'm a bit troubled as a scientist, like how stable are the insights that we gain by the experiments.
Right, there are methods developed by the AI community on interpretability, explainability, which can be used to a certain extent to open a little bit the black box, to look behind a little bit the black box. I agree with you. I mean, it's a concern. But we can put rail guards. We can, like the constraints, kind of at least make sure that, I mean, in this one project, that's what we do. We just tell, no, you cannot generate this token because there are some rules that will be violated. So we don't need to understand exactly what the system does, but we constrain what it produces. This is one way. Another way, I think, we need to move into more explainable methods. And this is my hope, for example, with the SSM models also. Their mathematics, so it's linear algebra, it's more explainable to begin with than the transformers. But this is speculative as how much this can help.
Thank you for your presentation. I have a question about the preventing intrusion into the model code that the large language model generated in important scenarios like hospital or driving scenarios.
I mean, personally, I haven't looked at privacy issues, but there are a lot of fellow researchers around the world that look at privacy issues with the
your
LLM.
large language model will provide a code, I think, generate a code for a user. So if the user scenario is related to the hospitals, it's a critical scenario, I think. I just want to know, do you have any perspective about the preventing adversary to change the code, to change the model that generated from the large language model.
So you are saying to change the model to ensure that the generated code is more privacy preserving, or?
I think it will be easy for the adversary to generate the code again and generate the model and change the model. I think this perspective is really important.
It is, absolutely. All I'm saying is I
Yeah.
haven't
Yeah.
looked myself and my team in this aspect, but it's absolutely
Yeah.
interesting and important. I mean, in the first
Yeah,
place.
I have another question about the hallucination guarantee. I think you check this based on you measure. I think it's how you measure this process.
Okay, so the method that we use is such that it guarantees that what is produced complies with the specification. Hence, it cannot hallucinate. And we checked ourselves manually. But there are colleagues that used a similar technique for ensuring that the generated code is type safe. And they went all the way to prove that this is the case, to formally prove. We didn't go that far. Right? And it's not also in our area, I think it's not viable to have formal proofs with these huge specifications. But we're saying the fact that we enforce compliance with the specification avoids hallucinations, because the model cannot generate API calls that are not specified in the specification.
Nice, thank you.
Kind of related to the same topic, so this constrained code generation. I was wondering, for web API specification, can these constraints be automatically generated, or are these manually?
They can be automatically generated.
Okay, so
I
you can
thought
just.
you are hinting at the problem that this is a rare luxurious case we have where specifications are available, and they can be automatically translated into constraints that we use. But in many areas, you don't have the specification. So.
Good. Any other questions? Maybe let me ask one, and maybe if anyone else has another one, we still have a bit of time. So in this work where you combine LLMs with graphs, I guess the assumption is that if you bring graphs that compilers and program analyses are using into AI-style reasoning, things are getting better, and your numbers are supporting this. I mean, I share this assumption usually, but just to challenge it a little bit. So when a human, for example, myself, looks at code, I do not think about ASTs, I do not think about data flow graphs, I do not think about control flow graphs, usually at least, right? So, and most developers probably, if you ask them to draw these graphs, they wouldn't even do it properly, except a few that are trained in program analysis. So shouldn't we try to make the models think a little bit more like humans instead of trying to make them think a little bit more like program analysis tools?
A very interesting question. But I mean, we don't, as a programmer, you are right, I agree with you that I don't think in terms of control flow graph. But when it comes to understand existing code, I do look at what method is calling which method, what data is flowing to where. And we have built in this kind of knowledge how to think about calling structure and data flow structures into compilers and static analysis tools for a good reason, right? They help us a lot to reason about the code as human, to automate this process. We do it when it comes to understand what is happening or why something is going wrong. So I think it is, we humans do this to some extent, and we have automated this process to some extent, again, with our tools, with code. So why not give them that knowledge also? I mean, they start with code. This is also automatically generated from the code, right? It's just another modalities, not pure text, not pure sequences of tokens, but graphs which are embedded into code, are implicit in the code. That's the idea. So the knowledge is there, but the way we provide the data to the model, we flatten it, which eventually, it's like eventually with the huge models, they are capable eventually to, this structure emerges probably. That's the idea. But we don't just know. And even if that's true, I mean, our study that started as a motivation shows that it's not probably true that they can recover this structure from the sheer amount of data. But even if it was true, the question is, isn't it a better alternative to teach them that knowledge with less data than let them recover it from huge amount of data? And basically, when I look back at the work that we did on code completion, the huge amount of data was one thing. But another thing was that we, the software engineers, basically extracted the representation. We designed the representation of the code that we passed to the ML algorithm. Nowadays, this is one of the strengths of the big, large language model, the deep architectures, that you don't need to do representation engineering yourself, feature engineering yourself, but there is something that you lose maybe also out of this process.
Okay. Yeah.
So this was one of the things that distinguished not only the huge amount of data, there are different algorithms, deep learning, we used clustering and so on. This was one difference, the thing that we designed the representation of the code, and the other thing was like we used only high quality data. We trained on Eclipse plugin code that went through the whole very strict evaluation process to enter in an open source ecosystem.
Cool. Okay, one final question to close off.
Thank you for the talk. I wanted to ask about this, the use of these state space models in agentic approaches. So you showed the trade-offs between transformers and the state space models. I wanted to know if you have any experiments on using those models in agentic approaches.
No.
Do you have any insights on, like, based on their strength, how would they fare in those applications?
It's a good question, because given that they come, I mean, the mathematics behind them comes from control theory, they might be interesting approach to agentic AI, because control systems are basically used to have effects in the outside world and are dynamic systems that react to the outside world. Yeah, but yeah, I haven't seen others looking at it yet. Not that I can guarantee you that I have that there isn't another work, but I haven't seen it.
Thank you.
Cool. Good. With this, let's close. And yeah, thanks again.
Thank you.